Chapter 7.3. Now, in Chapter 7.3, we're still estimating, but notice it changes. In the previous two sections, we estimated mu. Now we're estimating p. So let's have a refresher on what p is. It refers back to the binomial distribution, and lowercase p is the probability of success. And then, of course, failure is the probability of, failure, the probability of failure is known as Q. And what we need to remember is that once you calculate P plus Q has to equal 1. So what we are estimating, what we don't know, is the probability of success in a binomial distribution. Now, there's some assumptions that will be made, and those are discussed in these bullets. N, which is our number of trials, has already been selected for us. The normal curve is a good approximation. We will use sample estimates for standard deviation when necessary. What that means is population standard deviation is sigma, but if we don't have that, we can use the sample standard deviation, which is S. Now, one of the things that you'll be asked in this is, are your values justified? Well, here's how we find if they're justified, and this isn't going to make a lot of sense yet. This reads N, number of trials, times p hat, and we're getting ready to discuss what that is, has to be greater than 5, and n, your number of trials, times q hat, has to be greater than 5 as well. So let's talk about what p hat and q hat are. Now remember, in this section we are estimating p, the probability of success. We do not have it, so p hat is our best guess for p. I don't know why it's called p hat, so just chuckle and move on. So how we calculate p hat is R, which is your number of successes, divided by N, which is your number of trials. And then once you have p hat calculated, since p hat and q hat have to equal 1, then to find q hat, you'll just take 1 minus p hat. Because we will need the value of p hat and q hat in order to calculate the margin of error. Notice the margin of error is always z sub c, and recall that z sub c is this little table here that we used previously, times, and notice all of this is under the square root, p hat times q hat divided by n. Then once we calculate e, then we can create our confidence interval. Now notice I don't put mu here because I'm not estimating mu, I'm estimating p. So p hat minus e, p hat plus e, and then be sure and put p in the middle. So let's look at some actual examples. All right, if you will open your book to page 368, and I'm getting there myself, page 368, number 7. It reads, consider n equals 100, so I already put that there, binomial trials with r equals 30 successes. So here's my n and my r. Now, A says, is it appropriate to use a normal distribution to approximate the p hat distribution? Basically, it's asking us, are our numbers justified? All right, that's back on page 1 of notes. To see if they're justified, n times p hat has to be greater than 5, and n times q hat has to be greater than 5. Well, that means I need p hat and q hat first. So p hat is your number of successes, r, divided by n, or 0.3. And q hat, we know p hat plus q hat has to equal 1, so just 1 minus 0.3 is 0.7. So here's my p hat, here's my q hat. So are they justified? So first I need to ask myself, is n times p hat greater than 5? Well, n is 100. P hat is 0.3. So that gives me then, when I multiply 0.3 times 100, I will get 30. So yes, that is large enough. Then I need to also make sure that n times q hat is also greater than 5. Well, n is still 100, Q hat is 0.7, and when I multiply that, I get 70. So, yes, this is justified. All right, part B reads, find a 90% confidence interval for the population proportion of successes P. So I want a confidence interval that's 90%, but before I can get to the confidence interval, I have to calculate the margin of error. So my margin of error will be, I'm going to use Z sub C. So I go to my table, 90%, 1.645. 1.645 times, now I need the square root of P hat, which we calculated to be 0.3, times Q hat that we calculated to be 0.7, divided by N, which is 100. All right, now when you go to your calculator, you only need a parenthesis here and here. So, see if I can show you on the calculator how to do this. So we're going to do 1.645 times the square root is second x squared, and it opens a parenthesis, and opens a square root. My calculator automatically opens a parenthesis, so 0.3 times 0.7 divided by 100, and then I close my parenthesis and push equals. And I get 0.075, so I'm going to round that to 2 decimal places, so 0.08. So there's my margin of error, my confidence interval. Now remember, we're not estimating mu, we're estimating P. So that is P hat, 0.3, minus the margin of error, and the margin of error is 0.08, and then 0.3 plus 0.08. So then when I do those calculations, I get 0.22 and 0.38. And that's what it's going to be asking you to find. So now let's take that information and apply it in an application type problem so you'll know what to look for. Okay, it reads, a random sample of 188 books, so that's my sample, that's my number of trials, so N equals 188. So a sample of 188 books purchased at a local bookstore showed that 66 of the books were murder mysteries. So we're talking about murder mysteries. So when people came in, success was buying a murder mystery, and 66 times that occurred. So that's why number of successes is 66. Let P represent the proportion of books sold by the store that are murder mysteries. Now, the first question says, what is the point estimate for P? Because we don't know P. Well, the point estimate is P hat, which is R, divided by N. So I'm going to go to my calculator and do 66 divided by 188 and round to 2 decimal places, and I get 0.35. So basically I'm saying my best guess is that 35% of the customers buy murder mysteries. But we always have to consider the margin of error. So my N is 188. P hat we just calculated, 0.35. And then Q hat is 1 minus 0.35, which is 0.65. So I have my P hat and my Q hat. Now, when I go to calculate the margin of error, I need Z sub C. And I neglected to put the confidence until down here. So just kind of peek down here. You see that we're 90% confident. So I go to my table, and 90% confident is 1.645 times the square root of P hat, 0.35, times Q hat, 0.65, divided by N, which is 188. So I'm going to put all of that into my calculator and get 0.06. So now that I have the margin of error, I can create my confidence interval for P. and that is p hat 0.35 minus the margin of error, and p hat 0.35 plus the margin of error. So my confidence interval for p is 0.29 to 0.41. So my best guess is 35% of the customers buy murder mysteries, but I'm 90% confident anywhere from 29% of them to 41% will buy murder mysteries. And then you may be asked, is the normal approximation justified? And this is where it wants you to show that n times p hat is greater than 5. So in this case we had n was 188. Times p hat is 0.35, and when you multiply that you get 65.8, so that's definitely greater than 5. Then we also have to show that n times q hat is greater than 5, so 188 times 0.65 gives you 122.2, and those are definitely both larger than 5, so yes, it is justified. That completes 7.3.